Okay, so we're going to talk about the last section of Focus 1, which is topic 1C, on just thinking about what's the difference between a real gas and a perfect gas. So let's see. Yeah, I'm sharing my screen. So real gases behave as perfect gases as the limit of pressure goes to 0. So basically, as pressure goes to 0, force of collisions and force of the collisions with the walls for a gas go to 0. And so that makes sense that things would start to behave more ideally in terms of you wouldn't see any interactions. So you have deviations at high pressures and low temperatures. So you can think of that as the gas gets closer to conditions for condensing to a liquid, it's going to behave less perfectly. So as it starts to condense, clearly the interactions are getting very important. And then when it's a liquid, it's occupying a smaller space in the container. So when we think about deviations from perfect behavior, real gases have molecules that interact. And so that's the reason why you have this deviation. So if you have repulsive forces, it's going to force the system to have a larger volume, so it's going to expand. And if you have attractive forces between the molecules, it's going to compress it. So when we look in your textbook, on page 19, this graph at the top, 1C.1, looks like the graph for how a molecule would form. So you have a low in this well where the molecule would be interacting at a favorable distance. Well, it's really the same thing. We're not forming molecules, but you have attractive forces when you're at long distances. But then when you start to try to force particles closer and closer together, they start to repel each other because of their nuclei. And so you have attractive forces which are making the system occupy a smaller volume, and repulsive forces occupying a larger volume. So, yeah. So when we look at this next page, we want to think about that whole idea that gases can condense into liquids. So if you're above some temperature, you have PV diagrams, isotherms. So each of these lines has a constant temperature. So this is on page 20 if you'd prefer to be looking at your own book. When you're above some critical temperature, you don't have any liquid forming. So shows you that these isotherms up here, if you're at high enough temperature, look very much like a perfect gas equation, PV equals nRT, so it's a hyperbola. But they start to change as you lower the temperature. And this bottom part of the graph really shows you what's going on. So if we take a gas at 20 degrees, whatever gas this is, and look at the volume pressure relationship, as the volume decreases, pressure increases, which makes sense going from A to B. But when we get to C, you notice what happens. You go from C to D, and the pressure decreases, the volume decreases, but the pressure remains constant. And that's because you've gone below the temperature at which that gas can condense to a liquid. So if you decrease the volume rather than increase the pressure, you're forcing some of it into the liquid phase, so that keeps the pressure constant. So that's going to happen until all of the gas at C becomes a liquid at E. And then if you continue to try to compress it, the pressure is going to skyrocket because essentially you can't compress a liquid. So that just shows you that when we're talking about real gases, we have to think about under what conditions might they be so real that their interactions create a liquid. So usually one of the most common ways to express non-ideal behavior is with something called the compression factor, which is given a capital Z. So the compression factor is what's the molar volume of your gas compared to what the molar volume would be if it was a perfect gas. So we can calculate the molar volume of a perfect gas. So Vm equals just V over N, so the volume per mole of the substance. So the N is over here from PV equals nRT. So the molar volume of a perfect gas is RT over pressure. So if you put that in for the molar volume of the perfect gas, the compression factor ends up being the molar volume of this gas you're talking about times the pressure divided by RT. So when we look at page 20 and look at this graph up here, this is showing you compression factors for different gases and how they change with pressure itself. So as you go to zero pressure, they should all have compression factors of 1, because at the limit of pressure going to 0, all gases should behave ideally. So some gases like hydrogen never have compression factors lower than 1. They're always higher than 1. So that has only dispersion forces, so there isn't a lot of attractive interactions. Other things, though, like this is ethene, this line, at low pressures, you have an attractive interaction. And then as you continue to higher and higher pressures, you end up with that repulsive interaction. And so then the compression factor is greater than 1 when repulsion dominates, the system is larger, has a larger volume than a perfect gas. So if you look at that graph on page 20, will help you think about how a compression factor, if you were to measure it, could tell you a lot about the non-ideal behavior of a gas. So if we have non-ideal behavior, we need to be able to mathematically deal with that. So have an equation of state that's for this non-ideal or non-perfect gas. And one of the ways to do it is with a virial equation of state, where you essentially just add correction terms. So pressure times molar volume equals RT is the perfect gas. But now we're just going to multiply it by some correction terms either in terms of pressure or volume. So each of these equations could be used in the same way. And so the B and the C, they're virial coefficients that are determined experimentally, which correct for non-ideal behavior. So you could do either this virial equation of state as a function of pressure corrections, or this one as a function of molar volume corrections. When you look at this and look back to where we just were, and if you look at this equation, molar volume times pressure equals RT times Z. So molar volume times pressure equals RT times Z. Therefore, when you look at this virial equation of state, all these terms here are essentially Z. So P, V, RT, and then everything in parentheses. Is that correct? Or is that compression factor? So for a perfect gas, the change in the compression factor with pressure would equal 0, because the compression factor should be 1 at all pressures. So it's should be a constant. But for any real gas, if you're using the virial equation of state, dz dp, if you take the derivative of this with respect to pressure, you're going to get 0 plus b plus 2pc. So you're going to get a derivative that is not equal to 0. And so when you look at that on page 21, so on page 21, this shows you that for a perfect gas, the compression factor is always 1. For other gases, it's not. And so if you're below some temperature, you might have a compression factor that stays constant at 1. You call that the Boyle's temperature. So at some low pressure, your gas may have a derivative that's equal to 0, but it wouldn't be at all pressures unless it was a truly perfect gas, which we know doesn't really exist. So it's important to think that the virial coefficients depend on temperature. So if you're going to use this virial equation of state to correct, you've got a lot of things to think about. You have to think about what kind of gas is it. That'll determine the B's and the C's. What temperature are you at? Are you at a constant temperature so that the B's and the C's are staying constant? If you have a mixture, that just creates another whole crazy situation that you probably don't have B's and C's for mixtures of gases. So those coefficients are hard to determine experimentally. So read the Chemist's Toolkit on page 22, and let me just remind myself what it's about. Yeah, it's just about differentiation. So just about what is a derivative so that you can remind yourself from calculus that it's the slope of a line. So I'll let you read that. So we have critical constants. So when we looked at the graph on page 20, where we saw that below some temperature, our gas would condense into a liquid, that would be below these critical temperatures. So, or the critical temperature. So as long as we're above the critical temperature, you can use that virial equation of state. The virial equation of state is usually a more accurate way to correct for real behavior, but it doesn't give you a lot of insight into why the gas isn't behaving ideally. So when you look at this, you can't really say that the B's and the C's represent some physical property of the gas. So it might not be the best equation to use if you're trying to understand the gas's physical nature in reference to its non-ideal behavior. So often you can build a model that helps you visualize the physical difference between a gas and a perfect gas. And that's what the van der Waals equation of state is. So if we start out with PV equals nRT, I take V over here, and then the first correction we can make is for the repulsions. If the repulsions are significant, then the volume of the container is actually going to decrease essentially. So as you put more gas molecules in, they can't get close together. So some of the space is limited. They're limited to not occupy all the space because of other gas molecules. Same thing as saying that essentially they occupy space, but that's because they repel each other when they get into each other's space. So that's the first correction. And then in the second correction for the van der Waals equation of state, pressure is going to be lower if you have attractive forces. And so you can make a correction based on that, where the pressure goes down as a function of this parameter A. So B is a parameter based on whatever gas you have, and A is as well. So B is a measure somehow of the repulsive interactions, and A is a measure somehow of the attractive interactions. So we can also just rewrite this with our molar volume, which is going to be more common. So I just took it and divided everything by N. So if we look at self-test on page 24, it asks you to determine the molar volume of argon at 100 degrees C and 100 atmospheres using the van der Waals equation of state. So we want to look at this, and as we rearrange and try to solve for volume, what we're going to see, so we start with the van der Waals equation of state. And we need to separate volume out. So I'm going to multiply both sides by Vm minus B times Vm squared. So when I do that on the right-hand side, if I multiply, then the Vm minus B cancels top and bottom, and I end up with Vm squared on the top. And when I do that for the second term, the Vm squared cancels top and bottom, and I have Vm minus B left on the top. So now I just need to group all my terms. So I'm going to divide by P first, and then move all of my terms to the same side. So multiply through, where you end up then with Vm cubed and Vm squared B. And on this side, multiplying through here, you get the same thing, Vm over AP term, and then a B times A over P term. So you can stop if you want and just go through this derivation, just if I'm going too fast for you. So once you have expanded everything, take everything to one side, you end up with a cubic. And this cubic can't be solved very easily analytically, only some cubics can. So you're going to use an n-solve on Mathematica. And I should still have this up here. Nope, that's not the one, sorry. Yeah. Yes, so I got the constant A. Whoops, I've got to stop my share and then share again, sorry. Yeah, so I put in my A and my B, and I looked at the units. The units are all in atmospheres, decimeters cubed, which are liters, and Kelvin. I put in the temperature we're at for this problem, put in the pressure, put in the gas constant in the right units. So the gas constant has to be consistent with liters, atmospheres, and degree Kelvin. And then rather than solving, I'm going to do an n-solve, numerically solve. So in Mathematica, capital NS, and then everything in square brackets. So I start out by putting in the equation I want to solve. And I want to solve for when it equals 0. So you go equals 0. And I want to solve for the value of molar volume when that expression equals 0. So I'm numerically solving for the molar volume. You get 3 answers. 2 of them are imaginary, and so we know that the answer has to be the 0.298. And because we're working in liter atmospheres, we know that that molar volume will be in liters, which is equivalent to decimeters cubed. So that's down here at the bottom. Let me get rid of that. I don't know what I just did to my picture. Luckily, I'm done with my camera actually, so whatever I did to it won't be a problem. That's as far as we're going to go in chapter or focus 1. We're going to skip the rest. The rest of it, chapter or focus, talks about the complications of using real gas equations. So things like you get below the critical temperature and you get a condensation, and so then the equation doesn't work. So thinking about how limited equations are for real gases, just so you understand that the world gets really crazy if we have gases that deviate from perfect behavior. So in general, we're going to focus mostly on perfect gases as we derive equations. So that is it. We're going to start into focus 2. If I can get myself out of here.